Hi, my name's Elijah Hobbs, and today I'll be showing off a demonstration of the intermediate axis theorem. The effects of the intermediate axis theorem are caused when an object rotates about its intermediate axis. What I mean by that is, for example, take this rectangular prism that I've drawn. It has three principal axes, the x, the y, and the z. The moment of inertia is lowest about its y-axis, greatest about its z-axis, and it is intermediate about its x-axis. So along both its y and z axes, we will see typical rotation we expect if we spin it in air. But about the x-axis, we will observe a flip during its rotation. That is a bit confusing to understand at first, but it does not simply rotate about the x-axis. During its rotation, it will also flip around the y and z axes. We'll see that in just a second when I show a slow motion video of me flipping a book. At first you can see me showing off the axis system of the book to the camera. Then I'll flip the book and the video will switch to slow motion, and you can see that during its flip, it does not simply spin around the x-axis, but will also experience rotation about the other two axes. It looks a bit strange, but as you can see, as I've caught the book, the axis system has flipped from what it once was. Now that I've finished showing off a real-life example of the intermediate axis theorem, I think it's a good time to explore some data that I've gathered about the intermediate axis theorem. So all of this data was gathered by using a gyroscope in my phone, recording that data and processing it through MATLAB. The way I did this was I flipped my phone the exact same manner as the book, making sure all the axes flipped in the same way. So essentially this data is the same proportions as the book. It's just the scaling would be a bit different, but everything should line up in terms of where the angular velocities are increasing and how they're increasing and decreasing. All that should be the same. So the first graph that I've been showing for a while now is rotation about all of the axes with the intermediate axis theorem applying to the phone. So you can see for the x angular velocity, you can see it go up a lot and then flip from positive to negative and then stop, of course, once I catch it. And then you can also see some large spikes in the y and z axes. So that's what we're seeing with the intermediate axis theorem that we don't see with the normal rotations, those spikes and the other types of rotation. Because obviously when you spin around the other axes, there will be small disturbances in the other axes of angular velocity, but not as big as we see in this example. Next, we can begin to compare the axes individually. So what I did to get my second data, which should be without the intermediate axis theorem effect, is I essentially took my phone and then manually rotated it about the same time frame as was experienced with the intermediate axis effect to kind of show what happens if the phone were to rotate purely around the x-axis without any of the other effects, just to show the intermediate axis theorem effects. So this is me manually picking up my phone, rotating it around the same path that the phone originally experienced with the intermediate axis theorem effect, but with me preventing any rotation in the other directions. So we can see a clear difference in the rotation about the x-axis. We can see it's purely positive and that it just increases and slows down during the time at which it's in the air. But with the intermediate axis theorem effect, we can see that changing from positive to negative, which is a clear indicator of this effect. Next, we can look at the rotation about the y-axis, and we can see that large spike, which does not occur if it is purely rotating about the x-axis. So this is another clear indicator of the effect. And then again, similar to the y-axis as the z-axis, where you can also see that large spike, which is part of the intermediate axis effect, which is causing the object to flip about that x-axis. Finally, I want to address how exactly this is all related to aerospace engineering. So one big application of aerospace engineering is the design of satellites. And satellites can come in all sorts of shapes and sizes, but a lot of them can be cylindrical and a lot of them can be like rectangular prisms. And so whenever you have something like that, you really need to consider whether the intermediate axis theorem is going to affect your product. So one reason why a lot of satellites are made to be cylindrical and why that's very easy is because a cylinder only has two axes that it can rotate about that have unique moments of inertia. For example, in my drawing here, the y-axis has the least amount of moment of inertia, and then the z and x axes have the exact same amount of moment of inertia. So there's no intermediate axis here, so we do not need to consider the effects of the intermediate axis theorem at all. So it's very easy to model rotation for a cylinder because we know that it'll either rotate about the y-axis or the x or the z-axis, and there will be no flipping while it's rotating on any of these axes. However, if you were to make a satellite that was, say, a rectangular prism, you would need to consider that because if it got into orbit and started rotating about the x-axis, you could be seeing a lot of effects that you did not want to, it flipping, having sort of erratic rotation that you were not expecting. So that's something to consider with satellite design, is why we make a lot of things cylindrical and why that's actually important, and some of the things to be cautious of if you're making a rectangular prism satellite and why you may want to be very careful about its rotation during that.